Okay, let's get started. So for this morning's seminar, we're very happy to have D.Neuenfeld from Perimeter telling us about bounds on gravitational brane couplings and tomography in AdS3 black hole microstates.
All right, thank you. And yeah, so I guess I'm like the third person in a row who sort of like got shuffled around or learned on Monday that they are giving a talk today. So I hope this goes over well. Yeah, I'm talking about work which has appeared on the archive, I believe, last week. Oh, no, I'm doing something wrong. Yeah, appeared on the archive somewhere last week with Ji-Hoon Lee from Perimeter and Ashish Shukla from École Polytechnique. And so like the whole premise is more or less like motivated by work that appeared like last year and the year before with like those people from like Perimeter, Amsterdam, and Stanford. And I will, stay sort of like in the theme of yesterday, at least to some extent, by talking about end-of-the-world branes in holography. Now, as I guess all of you know, they've had some pretty interesting applications, in particular recently, more general speaking, as models for black hole microstates, or sort of bottom-up constructions in the AdS-BCFT correspondence. And then in the context of double holography, this first idea of black hole microstates was shown in like a nice paper by the UBC group that this can be used to like embed cosmologies into holography. And also the models, which I've sort of like showed by this funny picture, had or played an interesting role in the study of evaporating black holes, and particularly coupled to baths. And this was like one of the this is like an interesting model because it allows us, in particular in higher dimensions, to prove the island formula in these doubly holographic scenarios. Now, just a quick reminder of how those constructions usually work. From the bulk point of view, we have an action which consists of three parts. First, a bulk gravitational action, which is just Einstein-Hilbert gravity in my case. Then on the brane, we have two terms. We have a Gibbons-Hawking-York term, which is important to have a well-defined variational principle. And we have some tension term. Decided to rescale the tension in like a particular way, but I just call this parameter T0 here tension. And then we have a boundary term with, again, a Gibbons-Hawking-York piece and some counterterms. And in fact, it's the absence of these counterterms in the brane action which sort of give rise to gravitational dynamics in the end on the brane. Now, if you vary this action, then we get the standard bulk equations of motion, and we get boundary contributions. The one at the asymptotic AdS boundary vanishes because that's where we fixed our metric. So we choose Dirichlet conditions there, and on the brane, we want to allow metric fluctuations. So we want this prefactor here to vanish. In other words, we choose Neumann boundary conditions. And this is sort of like the one-sided equivalent of the Israel junction conditions, which were discussed yesterday. Okay, and all of this gives rise to double holography. So here, really quickly, my take on it. This is the construction I've just described, which is sort of like this bulk perspective where we have a gravitational spacetime, which is bounded by an asymptotic boundary down here and an end of the world brane up here. And then if we integrate out the bulk completely, we end up with the BCFT model where we have sort of like an ambient CFT living on an interval maybe, or a spacetime with boundary. And then there can be like quantum mechanical systems or other conformal field theories at its boundary. Now, what this parameter, like the tension parameter here, allows us is it can be tuned, and if we tune it to a nice critical value, which in my normalization is 1, what we're doing is we're pushing this brane all the way up to the boundary, and so it really sort of looks like an IR cutoff from the bulk point of view, or UV cutoff from the boundary point of view, if we had a CFT up here. And so that suggests a third effective description where instead of integrating out sort of like all the gravitational system here, we integrate out the region between the brane and the boundary, and we sort of pretend we can do holography on the brane. And it turns out that, well, two things really happen in this limit. One is there's a new mode of the graviton, at least in higher dimensions here in the bulk, which localizes to this brane, and its dynamics, which takes the form of the counter terms I would it, this is really the asymptotic boundary. So what we have here is a CFT coupled to a gravitational coupled to a gravitational system, which follows gravity with a massive graviton and higher curvature corrections, coupled to some sort of like effective CFT. Okay. Now, why am I saying all this? Oh, sorry. Yeah. Another important thing for the rest of this talk is that, of course, we can compute entropies in this model, and that's what many people here love and do for a living. We can do this by the usual Ryu-Takayanagi formula. However, in the presence of end-of-the-world branes, it gets a little twist, and that usually the Ryu-Takayanagi formula tells us, given some subregion A on the boundary, we can compute its entropy by the smallest extremal surface homologous to A. Now we're relaxing this homology constraint slightly, and that we're allowing the RT surface to end on the brane. Now, from the point of view of double holography, that's interesting because in double holography, this intersection of the entanglement wedge here, if this was the correct RT surface, would give an island and a doubly holographic description. And so, well, yeah, this intersection here would be the island associated with this bath region A here. Okay, yeah. So why am I saying all this? This is more or less all to motivate the interest in the following points. Namely that we have these models of double holography with end-of-the-world branes, and they have some interesting limit where they contain a semi-classical gravitational theory, which is sort of only an effective theory. But they have this additional power that quantum gravitation effects, like the island formula, can be understood from the bulk. And so that should be motivation enough to learn more about these end-of-the-world brane models. And there's a couple of questions we can ask. One is, for example, well, what's the dictionary for double holography in this brane formulation? And there's been sort of like a paper from last year where I discussed a bit an extraplot dictionary for the stress energy tensor 1-point function and used this to compute graviton masses. Then there's a question of, okay, how do we deal with the fact that we only have like this cutoff theory? There's like some small scale where we have non-locality. That's an ongoing project with a student at PI. But what I want to focus on here is sort of like another question, maybe just the fact that these end-of-the-world branes, they're effective descriptions. There are top-down constructions in the sense of like supergravity top-down constructions, where they correspond to like branes and string theory, which are back-reacted and so on. They're of course much more complicated. The compact directions of your 10-dimensional solution, they're warped in a non-trivial way. And so here we're sort of like throwing this all out and giving this very simple model just by a brane with Neumann boundary conditions. But in the spirit of effective field theory, what we should really be doing is we should allow for more general couplings on this brane. And that then opens up this question, well, what couplings or which solutions are actually allowed sort of from a UV point of view? So for the rest of this talk, I will focus on this question in sort of like a very simple setup and sort of give like a proof of concept that in fact we can use, well, quantum information theoretic arguments to bound additional couplings on those branes. In particular, I will focus on the case of a 3-dimensional bulk, and so a 2-dimensional brane. And I will focus on the case of adding additional gravitational dynamics localized to the brane. There will be, in my case, JT gravity. And well, if we add those terms to the brane, what do we do? Well, there's effectively two important changes. First of all, they change the location of where the RT surface can end on the brane. And second, they change the onset of a phase transition. Now, it's fairly easy to understand this if you know the following fact, that in the presence of those additional contributions on the brane, the phenomenon entropy is not only computed by an extremal area in the bulk, but if the RT surface connects to the brane, there's an additional contribution, which is, in that case, the Delaton evaluated at the intersection of my RT surface and the brane. And of course, I also need to the RT prescription now is to extremize this whole thing here. Okay, so a little plan. We're done with one, so giving a little review of end-of-the-world branes and double holography. Yeah.
Can you go back to the previous slide? So I just want to understand this JT action that you wrote down here. This is something that you are When you say 2D, are you talking about a 2D brane or a 2D bulk?
Right. So this will be just localized on the brane.
Okay.
Yeah, on a
So
2D brane. So I'm
it's
considering a
2D
3D
brane
bulk with a 2D
with a
brane.
2D brane.
And I, can write sort of like all sorts of like terms with like extra scalar fields or
Good.
like geometric quantities, which
Right.
are just localized to the 2D
So
brane.
you're adding some action to the brane action, which
That's
is
right.
going to change its equations of motion and everything like that.
Right.
And what is phi naught and phi here? Are these scalar fields that are like delta function localized on the brane, or are they limits of things that are defined everywhere in the
No,
bulk?
this is all just intrinsic to the brane.
Just intrinsic to the brane. Okay,
Yes.
thanks a lot.
But I mean, you're right. Just to like add a little comment, right? Of course, like you can ask a much more general questions, right? You can ask, well, what if like I add couplings to like bulk scalars, for example, to the brane? What would that do, and how would I sort of constrain those, for example? Now here, because I'm using computation of entropies, and because this computation is sensitive to those terms, that's why I'm discussing them, right? But of course, there's like much more general questions one can ask. Okay, so first point I'm done with. Now I'm going to introduce sort of like the exact situation I'm looking at, AdS3 planar black holes with these end-of-the-world branes, discuss sort of like the general solutions and the ones we're interested in. And then I'm going to talk about constraints on those GT couplings, and depending on time at the end, I will just like add a few words and change gears and turn this around and ask, well, if we have access to like entropies in the CFT, what's sort of like a practical way of getting back the JT couplings we decided to put on the brane? Okay. Okay, so the situation I'm looking at is a planar AdS3 black hole. That's just the metric with a blackening factor here. R plus is the horizon radius, L is the bulk AdS length scale. And what we want to do, we want to find solutions which cut off the left asymptotic boundary here and obey the brane equations I've shown on a previous slide. And they just like take, if you rewrite them a bit, they take like this very nice form where the extrinsic curvature is now proportional to the induced metric, and the proportionality factor is your tension. And we also want to use the translational symmetry of the planar black holes. So if you plug in the translation asymmetric ansatz for the trajectory of the brane, you get this nice equation. And we can just have a look real quick at sort of like all possible solutions. We can reparameterize this a bit and bring this sort of like to a particle in a potential like form, where you have a potential given essentially by the blackening factor, and you have a particle with energy given by your tension, and your brane trajectory is sort of given by trajectories of a particle in this potential. And we see there's three distinct cases here. One is where your brane.
Sorry.
Okay, I thought you...
I have a question. Yeah.
Yeah.
About the setup.
Yeah.
One advantage of double holography, right, is that the highest dimensional picture allows you to compute using just the classical area things that would require quantum corrections in the intermediate picture.
Yeah.
When you vary the gravitational coupling on the brane in the way that you generalize it by having this extra term. What happens to that relation?
Right. So I will not have to say much here. So what I'm going to do here is sort of just restrict the bulk solutions in terms of the BCFT picture. But to still answer your question, so in general, well, let me talk about maybe the higher dimensional case, because there it's a bit simpler. You get sort of like a leading Einstein-Hilbert term plus higher order corrections. Now the canonical choice of what you could add in higher dimensions is just, instead of JT gravity, just an Einstein-Hilbert term with a coupling you can tune. And that just modifies the effective, well, the coupling of this first term, of the Einstein-Hilbert term. So you can come, if you make a bad choice, you can come into a situation where you make the first term in sort of like this higher order expansion, like fairly like too small, maybe. And then you have like very strong higher order curvature corrections. And it would be interesting to understand, so like the bounds I talk about here, maybe from this perspective. But yeah, I won't have much to say about this.
So in the context of this talk, the motivation for considering double holography is not that the highest dimensional level allows you to compute quantum corrections.
No, like here it's really, we want, like, I would like to understand double holography better. And there are all these couplings you will add to the brane. Are there sort of like some top-down or like more fundamental UV restrictions on those couplings, which are visible?
I see. Roberto has his hand up, so while we're asking.
Yeah, I don't know, can you unmute yourself? Oh yeah, okay.
Yeah, hello. So I have a question. So if you just have the brane with the lowest dimension coupling, the cosmological constant, then in general, when you take the brane to the boundary, gravity on the brane disappears, right? Now, what I'd like to know is if you add these additional couplings on the brane, is there a way of sending the brane to the boundary and tuning the couplings so that you still get gravity at the boundary? You get gravitational dynamics at the boundary. I don't know if it's clear what I'm asking, but it's a general.
Yeah, I'm not sure if like you were, but like the volume was a bit low, so I'm not sure I fully understand your question. Let me say what I think I understood, and then you tell me what you actually said. So what I gathered is you were wondering if I add these additional couplings, can I still take the brane all the way to the boundary?
Yes, exactly, and get still dynamical gravity at the brane by tuning the couplings to particular values.
Right. So I mean, here I can just write down, and you'll see that I can just like write down solution in the two-dimensional case, and it works. In higher dimensions, you can also do this. You have to. So a very convenient way to do this is, in addition to adding, say, an Einstein-Hilbert term, you add another counter term to the brane, which you then tune such that it sort of cancels the contributions, like the onshot contributions coming from the gravitational coupling. Now, there is, of course, a question of like consistency. Do you at some point end up with like a brane with negative tension this way? And if that's consistent, there's another question, what this actually does to localization of the graviton to the brane. But yeah, like in principle, you can write down the bulk solutions. I mean, if you want to take like the most basic approach to what I'm going to say is really, I write down the bulk solution and I ask, can this be realized in a BCFT?
Okay. Okay, well, thank you.
Yeah. Dominic, this is, I think about the premise of Roberto's question and something you said earlier that I want to understand. Is the claim you're making, this is probably just something very standard, that in the limit as the brane approaches the boundary, the brane action automatically becomes the counter terms that I would need to define a UV complete theory of gravity?
Yeah, I mean, you get, well, the reason you add these counter terms usually, right, is because you get large contributions which would diverge and you need to subtract them out. Right, now, if you don't add the counter terms, you're left with these large contributions, and there's like a way of reshuffling things that you sort of can split the action you get into, you know, adding and subtracting the counter term, you get something which is like a renormalized effective CFT action plus a gravitational action.
Right, but the brane equations of motion, or the brane action, is the same thing as the counter terms, I guess, or in this large radius limit, the brane automatically adds in the counter terms for you?
No, so
Okay.
what happens is that, so like the gravitational dynamics are really like CFT loops at higher energies up to some cutoff. It's just like they take the form of, so like minus the, right? There's like a large contribution which you usually would have subtracted, and this large contribution is what gives you like your gravitational dynamics.
Okay, cool. I'll ask more later.
Okay, yeah, it's probably easier on the board. Okay, where were we? Right, okay. Yeah, so there's like 3 distinct cases. I just want to discuss for completeness. So we can imagine like a particle in this potential here, which starts out at 1, which is where our horizon is. And for tension less than 1, particle will bounce against the potential to fall back in. So that's the brane, which comes out of the horizon, goes away from the horizon up to some maximal distance and falls back in. There's a second one for t exactly equals to 0, where the brane comes out of the horizon and asymptotically approaches the asymptotic boundary. And then there's like other solutions for t bigger than 1, where the brane comes out of the horizon and just like hits the boundary at some finite time. And of course, there's like time reflected solutions to this. Now in pictures, there's like sort of like nice representations of those and crystal coordinates where you can write them down. And so clearly we're not really interested in this solution because that doesn't cut off the left boundary. We're certainly interested in the solutions with t naught smaller than 1 because they do cut off the boundary. And then there's like this intermediate case where it's sort of like a bit less clear whether you should also consider this or not. But it turns out that you can actually arrive at this solution by taking a particular limit of the solutions. There's like the naive limit where you just send the brane all the way to the boundary. That's not how you get this. But if you do this, while at the same time shifting or like doing a like a Schwarzschild time translation to your solution, you can actually end up at this solution. And so this is why I will be discussing those two solutions. Now, sort of, yeah. Sorry, from the bottom to there's.
I mean, this is a silly question. I'm just asking if you can go from the bottom to the top through the bifurcation surface with the brane. Can you make such solutions?
Sorry, I'm not.
So just take your first picture and shift it to the middle.
Oh, I mean, what you?
Can you cut out the bifurcation surface with the brane?
Not quite sure what you mean by bifurcation surface of the brane.
Yes.
Oh, I see. Yeah. So, I see. Yeah. So, I mean, if t naught was equal to 0, the brane just like sits in the center, and you would get like a Z2 reflection symmetric situation. And I mean, that's something people have studied. It's models of like microstates. That's not necessarily like interest. Like you wouldn't be interested in this if you were interested in like cosmological applications of this.
Is that the case when you have a lot of sort of higher curvature corrections coming in?
Yes. Yeah. Exactly. Okay, yeah, just so last comment on sort of like cosmological applications and holography. The first case would be a Big Bang, Big Crunch scenario in like a space with negative cosmological constant and some radiation. Well, in fact, all of those have radiation. The second one, which is also the one I will be discussing, is a flat universe with 0 cosmological constant and radiation. And the one I'm sort of ignoring is a solution which has radiation and either a late or an early time, depending on which solution exactly you pick de Sitter phase. Okay. Also, just one other quick comment. Like the reason, of course, they're black hole microstates is because you can compute entropies and the entropy vanishes. There's like a very nice and easy way to see this is you construct them using Euclidean constructions, which can be done easily for these like time reflection symmetric cases. However, again, for like cosmological applications, there are some subtleties in that you might not be able to construct Euclidean solutions where you can push the brane all the way to the boundary and so on. And then you might start thinking about, well, how might I be able to do this? And there was a recent paper by Chris Waddell who argued that that can be done if you add additional gravitational couplings to the branes plus additional defects in the bulk. I think also Simon had like a paper on those questions. And so that's sort of like maybe another motivation for like a general, generally to understand what kind of additional couplings can you add? Because in the solution of Chris, you had to add like negative gravitational couplings to the brane.
Yeah, because you mentioned DGP. This is similar to DGP, right?
Yeah, I actually didn't want to write DGP here. But yeah, so I mean, I would think of this as the 2- or 3-dimensional like generalization of DGP.
Yeah, so that's why I think maybe a little bit this is too, but what you're doing is essentially something. Suppose you have a like Planck brane, the cutoff brane, you have a big kinetic term or negative, so you try to constrain this brane localized gravity kinetic term.
Yeah, exactly.
And usually, they did the phenomenological strongly coupled, blah, 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 right? But now you imagine that the bulk has a black hole. Then you can have a second mass. And then there you can have asymptotic boundary.
Exactly.
And you can view this is a CFT and the original cutoff things to be end of the world brane. Then you can use the BCFT to constrain this thing.
Yeah,
So
exactly.
you don't need to be the 3-dimensional or 2-dimensional if you are allowed to be like these two-sided black holes.
Yes, there are technical reasons why I do this here. And well, let me say them now then. One is because here I can do stuff essentially analytically, which in higher dimensions is going to be more complicated. And then you might say, well, you just do it numerically. Who cares? But the second thing is, it's hard in higher dimensions to find tight bounds. Now I'll explain in a second why. So the bound explicitly we're using here doesn't carry over like very easily to higher dimensions.
Because it's an explicit technique you use may not. But if you could do in a higher dimension, you can compare that with the bound people doing in a higher dimension. and so on,
Absolutely, right? I mean, like part of this is sort of like to motivate it. Like this is a proof of concept. It's in principle possible. There might be like many other different useful bounds, and it would be interesting to know what to look for.
Thanks.
Okay. The point is, I will like bypass all of those questions about Euclidean continuation by just saying we have Lorentzian solutions, and if you get there by Euclidean continuation, well, that's good. And if you don't, then maybe you haven't worked hard enough, or maybe there's other ways of getting them, or they're not, easily obtained by analytic continuations. Okay, yeah. So the question we want to ask is, do these states or these solutions exist as CFT states in AdS holography? And the strategy we want to follow here is, well, we know that from the asymptotic boundary point of view, the CFT states locally look thermalized, just a black hole horizon. But if you look at very large regions, then the entropy might have non-trivial time evolution. And this time evolution is subject to bounds and very restricting bounds. And so once these bounds are violated, we can say, well, this state is certainly not a good CFT state. And we rule out the corresponding bulk solution. The intuition very roughly is this. If I add JT gravity or maybe like BGP terms and more general to the brane, then things like this could happen where I make the region I'm interested in at the boundary like a little bit forward in time, but my brane or my RT surface actually sweeps out a very large region in the corresponding bulk, and that might give rise to like large changes in entropy. And if they become too large, again, we can rule out those couplings. Okay, so what are those bounds, or the particular bound I'm interested in? It's a bound on entanglement velocity. So that's just velocity in quotation marks because it's not really a velocity. It's just a rate of increase of entropy normalized by the equilibrium, entropy density, and the volume of the boundary. And there's a bound in 2 dimensions, which can be shown very rigorously. That it's bounded by a function of the volume of the boundary region you're looking at. Now, if you're looking at sufficient, well, we're in a planar black hole scenario, so we can look at arbitrarily large boundary regions. And so in particular, we can bring this bound down to the bound on the entanglement velocity, which is, well, entanglement velocity has to be smaller or equal to 1. Now, I should say, well, 2 comments here, maybe. First of all, I just want to make sure that, or point out that usually entanglement velocity, or very often, it's discussed sort of in the late time limit at times larger than beta. But here we're interested in like a strict bound which holds at all times. And this is precisely the point that you can prove this bound in 2 dimensions at all times, but not so in higher dimensions. And the technical reason for this is, well, in the proof, and the proof is due to Nima Afkami-Jetty and Tom Hartman. In the interest of time, let me maybe be very brief here, but it's essentially based on monotonicity of relative entropy. So you take some region B and you take some region A, which is contained within the domain of dependence of B, and monotonicity of relative entropy tells you that the relative entropy of this region A with respect to the thermal state, that's what I choose here, is smaller than the relative entropy of the state B with respect to the thermal state. Now, we can rewrite the relative entropy using the first law, or like by the first law of entanglement, as a difference between entropies minus a difference in modular Hamiltonians. And this is exactly where it becomes important that we're in 2 dimensions, because we're here interested in the modular Hamiltonian of a 2-dimensional CFT in the thermal state. And so that's known, that's the local integral of the stress energy tensor. And so we know that in our case, those 2 terms here, whether I'm in the thermal state or in a state with an end of the world brane, just cancel. and the modular Hamiltonian cannot tell the difference. In higher dimensions, we don't know the explicit form of the modular Hamiltonian. In vacuum, we know, but not in the thermal state. Right, and so we cannot run this argument, at least at early times. There's arguments for late times, but that's not going to be sufficient for us. Yeah.
Why did you, I didn't understand why you said these two modular Hamiltonian terms cancel. We know it's a local integral of the stress tensor.
Yeah.
And we're evaluating its expectation value in two different states.
Yes.
Why do we know that that's the same?
Because the geometry of my two solutions is exactly the same outside the horizon, where I evaluate this like at the boundary.
I see. So the expectation value of the stress tensor
It's
near
just
the
the
boundary
same in
has to
both
be the
states.
same.
Yeah.
Okay, great. Thank you.
Okay. So if we use this and plug this into the non-monotonicity condition, then after a little bit of algebra and plugging in the correct values, we just get precisely the local bound I was talking about before. And so this is now the bound we want to check. Now, before we do this, let me just remind you of like a few subtleties which are important in computing RT surfaces. So there's two candidate RT surfaces I mentioned before. One, which I will call the disconnected phase, is just like the usual RT surface which computes the thermal entropy of an interval. And so you have your area functional, you look for an extremum. He has boundary terms generally when you vary this, but those vanish because you fix the endpoints of your interval. And then if you plug in your solution and divide it by 14 Newton, you get the usual expression for the thermal entropy. Two things to keep in mind here. First of all, the solution is time independent. Second of all, it's, at least for large enough A, it's extensive in A. So if I make this region larger, the entropy becomes bigger or the area becomes bigger. Now, there's the second solution here. In deriving this, we make use of the translational symmetry. So we know that our RT surface like falls straight through the black hole and touch on the brane. Now, the general solution to this is given in terms of some conserved quantity, which is given by this expression, and can be, and again, that's a benefit of the two-dimensional case, explicitly just like written down using a simple function. Now, here, differently to the previous case, if we do the variation, then again, we fix our endpoints here at the asymptotic boundary, but we don't want to fix them on the brane. And what this does for us is, well, it's fairly easy to show that the contribution, the boundary contribution you get is proportional to this charge here. So we want this boundary contribution to vanish, or in other words, we want this charge to vanish. And that's for the case without JT gravity. Now, we will see in a second that if we add JT gravity, this charge here now is set by the derivative of our Delaton on the brane. And this is sort of how we get now different answers for the entropies of subregions A. Similar comment as before, well, here the solution is independent of the size of A, but it depends on time, essentially due to the cutoff near this boundary. But this is important that for essentially arbitrary late times, because we're in a planar black hole scenario, this here can be made the RT surface just by choosing a sufficiently large region. All right, so I can always go to the scenario where this here gives me the smallest extremal surface. Okay, so let's start subcritical branes and the vanilla case without any JT. Here I've just drawn a bunch of RT surfaces. Here's the brane, here's my boundary. They just follow straight lines in crystal coordinates. And we can look at the renormalized entropy as a function of the boundary time. And we see, well, the derivative here, I've normalized things such that if the slope here is 1, entanglement velocity is 1, it's fairly easy to see that the entanglement velocity here is just bounded from above by 1 and asymptotically approaches 1. So this is a wonderfully consistent state. Great. Now, let's add JT to the brane. As I mentioned before, this modifies the area functional. Now you see that if you vary the area functional here, you get your boundary term, which is evaluated at the brane. Before, the variation needed to vanish. So this would set this charge QE to 0. Now the value of this charge QE needs to cancel a contribution, which comes from the contribution of the Delaton. And so if our Delaton is time dependent, this will also make this charge time dependent. In terms of the solutions for JT, well, we can now set, so that sort of addresses Roberto's question of it, we can set the location of the brane by choosing an appropriate cosmological constant for JT as related to the brane location like so. And then the equation of motion for the Delaton takes the general form like this. There's an inhomogeneous piece, which can be solved for explicitly. And then we have a free parameter, phi1 here, which multiplies sine of tau, where tau is the time on the brane, which goes from -pi/2 to pi/2. And so we see that depending on where our RT surface ends on the brane, the solution will be different through this parameter QE and the trajectory. And yeah, right. The one important thing I should note here is now in the following, I will group this coefficient here, which is phi1 multiplied and divided by the bulk and the brane Newton's constant, and just call this alpha. And that's exactly the thing we want to constrain. Now here are examples for positive values of alpha. I've chosen positive values because negative values can just be obtained by using time reflection symmetry in the solution. So there's a symmetry if send alpha to minus alpha, time to minus time, you end up with the same solution. So it's sufficient to look at positive alpha. And you see the following thing. So if we increase alpha by a bit, then these RT surfaces, which start at fixed points on the brane here, start bunching up towards the past on the asymptotic boundary. And once we hit sort of like a critical value, they start falling into the past singularity. If we look at this as a function, or like the entropy as a function of T boundary now, then we see the following picture. Here, I've done this for two different values of Y brane. One is like fairly close to the bifurcation surface. One is a bit further away. Blue is vanishing alpha, and then green or olive is larger, and orange is the largest alpha here. We see that although the asymptotic behavior is still the same as before, so we approach an entanglement velocity of 1, at early times, there can be a phase of very large, like superluminal, if you will, growth of entanglement. Now, how do I turn this into like a strict bound? Well, one way of doing this, which is fairly convenient, is to just realize, well, if I look at the asymptotic expansion of this towards the future time, then if I'm in this situation, my solution, or like the entanglement velocity, will approach 1 from above. And so I want to rule those cases out. Now you can do this explicitly, and you find that the asymptotic expansion contains those two terms. And that gives you a bound on the value of alpha, which is given in terms of the location of the brane. You can repeat the whole analysis for negative alpha, and you find that the absolute value of alpha is bound by this function. Now, there's another thing with these RT surfaces going through the singularity, and I want you to take this with a bit of a grain of salt. Namely, the fact that the RT surfaces can leave this patch through the singularity, and the fact that we're in AdS3, where really the planar black hole is just a coordinate patch of the global solution, suggests that if we analytically continue our solution, there's sort of like a previous universe where we can have RT surfaces which come up through the singularity and hit the boundary where we are. So what happens if we also consider those RT surfaces? We can again draw a similar picture. Now I've plotted the entropy as a function of tau boundary. So it goes from -pi/2 to pi/2. And we see that those surfaces only exist for for early times. At some point they stop existing. And second, that they actually give the smallest extremal surfaces. So if you believe those solutions and RT, then you would have a discontinuity in the entropy because RT instructs us to take the smallest extremal surface. Now these, of course, also should be ruled out. Well, how do we do this? One way of doing this is to realize that RT surfaces define a map between tau brane and tau boundary just by following the RT surface. If RT surfaces don't cross through the singularity, this map is 1 to 1. If they do cross, this map is 1 to many. And so we just need to identify the point where the map turns from 1 to 1 to 1 to many. And that happens if this function obtains a saddle point. So we're looking for this condition, the derivative of T boundary with respect to brane should vanish. And that gives us another bound, which looks very much like the previous bound, except that now the plus down here is replaced by a minus sign. Okay, so in summary, we have those two bounds. One, which I would say is like very solid. Entanglement entropy is too fast. Now, if we are interested in like applying this to doubly holographic scenarios, we should be looking at what happens if we push the brane out to the asymptotic boundary. It turns out that this bound here actually becomes very weak, and well, it bounds alpha by infinity, so that's not very useful. This other bound here becomes it's very strong and strict, and yeah, places a bound of 1/2 on the absolute value of alpha. Now again, you might say, well, this is nice, it's a strong bound, but do we actually want to trust this solution? And the only comment I have to make here is that in higher dimensions, you actually run into similar configurations of RT surfaces, but now around time t equals to 0. Now, whether or not they actually give you a tighter bound, I have nothing to say about this as of now. But this is, you know, maybe to be like, to look out for those situations where you have unexpected RT surfaces. Okay, now we can repeat the whole analysis for critical branes. But if we do this without JT couplings, then we just find that there's no RT surfaces which connect the brane to the asymptotic boundary. Again, from like a doubly holographic point of view, it's like these flat universes with a zero cosmology constant, they don't have islands. So, well, what can we do? Give up? Well, let's add some JT gravity to the brane. Now with zero cosmology constant, and on top we add another like tension term here. And it turns out that the solution now to the equations of motion from this action take the following form. We have a Delaton, which is some constant, plus something which quadratically grows or decreases depending on the sign of alpha critical here as a function of the proper time. So lambda here is the proper time along the brane, which in that scenario, this is like a big bang cosmology. So we start here with lambda equal to 0 and it goes all the way up to lambda to infinity at the top. Now, there's a difference here, a qualitative difference, if we choose alpha to be negative on the left or positive on the right. Alpha is negative, like here on the left. We see that now we have RT surfaces which connect the brane to the boundary. And so we can in principle place bounds. If we choose alpha to be positive, the RT surfaces fall into the singularity, and then we're sort of like back at the discussion we had, I gave previously about RT surfaces falling through the singularities and considering sort of like RT surfaces which come from the past through the singularity and attach here to the asymptotic boundary. So we can again run through this whole same analysis, and it's very analogous and straightforward to show that now again we have here, now it looks like a bit less pronounced, the same asymptotic behavior that the entanglement velocity approaches 1. It's very late and very early times. However, here we see that towards earlier times, we can again, here in orange, get a phase if alpha is too negative of like fast growth or like too fast of a growth of entanglement velocity. Now this is before it was like on the other side towards positive times. Here it's towards negative times, just because we're at negative alpha. And we can do a similar analysis and just see that this critical alpha is bounded from below by -2 for the case where alpha is negative. We can also consider again RT surfaces which come through the singularity here and attach to like some region below critical time on this boundary. And this gives a very strong upper bound of alpha critical smaller than 0. So in summary, what we find is that, well, again, two bounds, entanglement velocity is too fast, so alpha critical is bounded from below by -2, or new RT surface alpha critical is bound from above by 0. There's another way of obtaining these bounds. I just want to mention here. I said before that this critical solution is obtained by a particular scaling to the subcritical solution. And you can go through the algebra and see how like different parameters and so on are related if you do this. And what turns out is that the correct scaling you want to do is you want to shift your time by t bar up here, whilst keeping e to the time shift times cosine squared of y brane equal to a constant. And this implies that alpha critical in this solution here is related to the alpha in your subcritical solution by this relation by a y brane dependent coefficient. And it just turns out if you now like put the bounds in for alpha we've obtained previously and send the brane all the way to the boundary, then you get those bounds back. In fact, you get slightly stricter bounds, namely that alpha critical, or the absolute value now, is restricted to be less or equal to 2. In the case where we're just interested in entanglement velocity, or if we also considering these RT surfaces through the singularity, alpha critical just has to be strictly 0 in those cases. Okay, so that's everything I want to say about brane tomography, about the bounds. I think I've a few more minutes to talk about the tomography part of it. So now I will just change gears a bit and ask a different question. And the question is just, now that we have the solution, well, if you give me the time-dependent entanglement entropy of like, say, a region, how could I actually compute back all the coefficients that went into my solution? So in a way, it's like a glorified inversion of some complicated formula, but this is a way to do this more like practically. So what parameters are we interested in obtaining? Well, one would be the constant piece of the Delaton. Second, this value of the time-dependent part of the Delaton alpha. Third, the location of the brane. And fourth, the parameter T0, which hasn't really made an appearance yet because I set it to 0 throughout the discussion. But this is just a time shift. Like this is a parameter which essentially tells you where the minimum of my entropy is, more or less. So there's a family of solutions which are obtained by shifting my solutions in time. Okay, so one way of getting at this is again to use entanglement velocity, in particular its asymptotic expansion around very late or very early times. There's sort of like the following protocol you can follow. First, you started looking like late time or early time behavior of the entanglement entropy. That depends on the sign of alpha. Like why you have to do this is a technical reason, and if you're interested, I can tell you after the talk. But the point is you get the sign of alpha fairly easily just by looking at the minimum of your entropy, and this will be generally not very symmetric but skewed. And depending on which way if it's skewed towards early or towards late times, the function there, you can read off the sign of alpha. Now these case here, they of course not invariant under shift in Schwarzschild time, but they transform just by multiplication, or at least K1 just by multiplication by an exponential factor. And so in order to get rid of this dependence on this time shift, we can form particular invariants of those coefficients. Now the particular invariants here are chosen such that the numerator has the lowest power possible in sign of y brane. Or in other words, they're like just convenient to work with, also numerically. And so it turns out that those invariants only depend on alpha and y brane. And so what you can do is you can either numerically invert this function, but there you really want to have help from Mathematica, or you do it like here and you plot your parameter space in y brane alpha, and you do a contour plot for like some random given values of LF1 and LF2. Now here I've indicated in black the exclusion of the weaker bound. Gray here is the region that would be excluded if we use this stronger bound. And we don't really have a proof for this, but we sort of extensively look at this numerically. And there is only one intersection of those contours. So from this, you can read off alpha and y brane. Now, once you have alpha and y brane, you can get this parameter T0 by just realizing that whatever your first coefficient in the asymptotic expansion of the entanglement velocity is, it's just related to an expression you can explicitly compute times this exponential of T0. So you can solve this for T0, get this coefficient. And then the last thing you're left with is just the constant piece of the Delaton. But this can, for example, be obtained by taking any reference solution with any constant piece of the Delaton and computing the relative entropy of this with the thermal state and compare the result of that to your particular solution you have. And so at the end of the day, you can actually fairly easily get all of those coefficients back from the behavior of entropy at the boundary. Okay, yeah, so I come to my final comments. That was a bit quicker than I expected, but I think at least some more time for discussions, hopefully. So there's, of course, like much more to do here and many more interesting questions. The obvious thing that was already asked for is, but what's the situation in higher dimensions where we have DGP couplings on the brane? Maybe more generally, not only sort of like the very naive thing you would add by just Einstein-Hilbert action, but you could imagine just adding a very general expansion and higher curvature corrections and see if you can place bounds on those. And then, of course, that was already also pointed at, well, now, do these bounds actually mean something from the point of view of double holography? Or are these sort of like, swampland-like bounds, which you can't really see from the effective theory in double holography, but just the fact that it's that there is a UV completion of your theory imposes those bounds. Then, as I also already mentioned, there are some constructions which actually use negative DGP couplings and additional defects and so on. And it would be interesting to try to rule out those constructions, or maybe not, maybe say they're actually nice and balanced. Then, of course, can we generalize this? So are there other inequalities we could use to maybe place stricter bounds? One example in particular for entanglement velocity is there's bound shown by Mark Mizzi a couple of years back about the early time behavior of entanglement entropy. Now, in this specific case, it doesn't seem to give any tighter restrictions, but it'd be interesting to revisit this in the higher dimensional context where it might be more powerful. And yeah, and also there's of course like all sorts of terms now you can add. You can add intrinsic like scalar fields, gauge fields, whatever, or couplings to bulk fields, and it'd be interesting to also bound those quantities. Yeah. Thanks.
Questions?
Can you just remind me why did you get rid of the last subcritical, so to say, case?
Sorry?
Why did you get rid of the third picture when you had all the three pictures? One was subcritical.
Oh yeah,
critical.
so I mean the logic here, let me go all the way back.
Sorry.
Yeah, no worries.
Should have asked before.
I mean, the logic here is that you can understand these solutions as particular CFT states, but that interpretation, and then you can look at entanglement properties of the state and place bounds on it. That's what I've done. Now here, like it doesn't really seem that you could actually interpret this as a state on like a single CFT because you have the second part here of the asymptotic CFT. Now you could maybe try to like add a second brane which cuts off this upper piece, but then you're still left with this like kind of like funky location here where the branes hit the boundary. So not really sure what to do with this. To me personally, that's like a very vague comment. This more or less, well, if you did that, that rather seems to be like some generalizations of these stories about projected black hole interiors, which like I think Ahmed Almeri, for example, discussed like a couple of years ago in the two-dimensional bulk context. And so, this is something one could, try to think about now in like a higher dimensional context using those solutions.
Okay. But there is no clear sign of what the cosmological constant would be on this brane?
Sorry?
Is it a clear sign what the cosmological constant would be on this brane?
The cosmological constant is positive, here.
It's positive.
It's positive. So this is negative, 0, positive.
Right. Okay.
Yeah.
This is very much like your thing from yesterday,
Yeah,
right?
yeah, that's why I'm asking.
Yeah.
Okay. Thanks.
To follow up on Maria's question, in your left picture, I understand how to construct the state
Mhm.
using a Euclidean path integral.
Right.
Fine. I certainly don't understand how to do that in the right picture, but I think I don't understand how to do it in the middle picture either.
How to do?
How to do that in the middle picture. So the middle picture doesn't have a surface of time reflection symmetry.
Right.
So you say that can be interpreted as state in the field theory. Yeah, probably. But do you have a good understanding of what state that is, how I might construct that
No,
state?
no, exactly, right? I mean, so this is why I made this like point somewhere in the talk of saying, I will not care about this right now. I will just pretend that, maybe there are solutions and I will see, are they actually? Now, again, you can sort of, well, it's not like in the construction, the Euclidean sense, but you can actually get this solution by starting with this solution, shifting it in Schwarzschild time, and at the same time, like putting the tension to 1. So there is sort of like a way of getting from here to here, but sort of like a direct thing where I can tell you, that's like boundary conditions or whatever you have to put in Euclidean path integral. I don't know, and particularly because it doesn't have a point of entry, as you say, right?
Yeah, I see what you're trying to do there. I'm a little uncomfortable with it because of the infinite time translation and the danger that this semi-classical picture is going to break down as you do that. But just to be practical for a moment, say that is some state. Can we figure out how to extract some information about how that brane is encoded in that state? You remarked that there's no RT surfaces that end on the brane.
Right.
So the usual thing that I would try to do doesn't look like working.
Yes.
Do you have any ideas about how to try to extract some information about the brane from this state?
Right. So in that specific case where you don't have additional like JT coupling, I don't have a good answer.
Okay, but you say
But
if you add the
point
JT
is,
coupling.
so I was maybe a bit brief, but this whole point of this like brain tomography was that you can do this, and in fact, if there's now a JT coupling with like negative, negative alpha critical, what I called it here, then you can in fact do this. You can, again, like by a similar protocol, you look at, for example, or I mean, generally speaking, there's like an infinite number of ways, but a very practical way would be to look at entanglement velocity and its asymptotic expansion, and then you can like compute back what your solution is.
So just as a follow-up, I mean, maybe I didn't really understand Simon's question, but about whether this middle thing is legitimate or not, I mean, if the theory admits an end of the world brane with this tension, then I don't see how we can exclude, I don't see the relevance of the question of whether you can construct the state via path integral or whether there's time reflection symmetry. If it's a classical solution to the theory, you can't really exclude it, right?
No, I agree. I mean, that's why what I just said, I look at Lorentzian solutions. I don't care how I get them. These are all the ones there are with the symmetries I wanted to look at. And so let's look at it.
Yeah, I have a slightly different question. So about this holographic entanglement velocity calculations.
Yeah.
What if we consider just a gravitational theory without an end of the world brane?
Sorry, gravitational?
Just a gravitational bulk theory without an end of the world brane. Right. Can you show that then they are satisfied?
I mean, it depends exactly on like which question you're asking, but so one thing that was done like by Hartman Maldacena, for example, in their paper was essentially this question, right? You would treat like the left boundary as some reference system, the right boundary as like the thing you want to involve in time. Then you look at RT surfaces, which go from a particular interval at a particular point in time on the right to the 0 time on the left picture. And yeah, and you can do this computation, you see these bounds are obeyed.
But I mean, what if we don't have the other boundary?
Well, I mean, if you don't have the other boundary in this specific context, you will just get a time-independent entanglement entropy. It's like the thermal entropy you get.
I guess what I have in mind is sort of rephrasing the question about the end of world brane in the gravitational terms. So if I have a geometry which caps off.
Oh, I see. So let's see. I mean, there is some literature on sort of what that tells you about the bulk geometry, and I am not aware of a paper which like specifically checks the solution for like early times of like t order of beta. But there's, for example, a holographic proof again by Mark Mizzi, where if you assume like the null energy condition in the bulk, that the bound on the entanglement velocity at late times is obeyed.
I see. I mean, I guess one would hope that just using the null energy condition, it would be obeyed at all times, but maybe that's just hard.
It might actually be, but
Right.
I mean, the point is you don't have this bound at early times, or you don't know how to prove it, right?
Oh, I see. So it's not something that we expect to be true necessarily.
Well, I think people expect it to be true.
Uh-huh.
It's just hard to prove. But okay,
You
no,
mean
I
from
should
the
say
boundary?
that probably, well, I don't know. I would have to look it up, but presumably you're right that if you do this holographic computation, then you can construct things which obey this bound at all times. But in higher dimensions, as far as I'm aware, this bound is just conjectured. So the entanglement velocity is conjectured to be bound above by 1. And there's no sort of like CFT intrinsic thing or CFT intrinsic proof we know of. And so, I mean, yeah, I think we expect it to be true, but we don't know.
Right, but the boundary could still be 2D, but the
Yeah.
bulk could be higher D, right? I mean,
Right.
if you're going to have it cap off, you know, you can have it cap off in some. in
Right,
fact, you-
right. Yeah,
right.
I'm not
So
aware of.
you could be doing a calculation or trying to do a bulk proof,
Yeah.
which is, you know, just using the null energy condition, but in
Right.
higher dimensions of an inequality which you know to be true, you know, for a 2D boundary.
Right. No, yeah, exactly. So I mean, this is what I was talking about. This is what Mark Mizzi did without any of the world branes, as you suggest. Yeah.
More questions for Dominic? Okay, if not, let's thank him again.